Okay, hello. I think we can start. I have some technical problems with headphones on my PC, so I just connected the laptop additionally. So this is why you can see me twice, and I will give you the presentation from different source than you are hearing my voice. So are you able to hear me at first? First important question.
Yes.
Okay, so right now I will just share my screen from the second PC. And you should see the presentation right now.
Yes.
So we just stopped with receivers, I mean signal receivers. Am I correct? This was the last slide summarizing the photodetectors. So the next active fiber devices are optical amplifiers, and they are quite important devices regarding the telecommunication and transmission systems, but not only this type of the systems, because optical amplifier, especially the fiber amplifier, it is also a base to produce, for example, fiber laser. On the next lecture, I will show you also something connected with these fiber lasers. So it is important to understand how fiber amplifiers are operating and what are the parameters of such amplifiers. But of course, the main application of such amplifiers is to just have something which allows to extend the transmission ratio, transmission distance in some fiber links. You can imagine, you know already the attenuation of the fiber. For the third telecommunication window, it is something close to 0.2 dB per kilometer. So it means for, let's say, 20 kilometer of the 100 kilometer of a distance, we will have attenuation equal to 20 dB for such a fiber. So if we want to have longer transmission distance, we need to regenerate a signal in a fiber in some way. Before the optical amplifier, let's say, development, there was so-called electrical regeneration systems. They were just typically some receiver, then electrical amplifier, and then transmitter. Yeah? So this was the device to just optically regenerate the signal. But we had this conversion to electrical signal, amplify it, and convert it back to optical signal. So the optical amplifiers allows us to just regenerate the signal in fully optical way without any change to the electrical signals and so on. So it is quite useful device. And of course you have some basis for understanding the principles of operation of such an amplifier, because all the quantum effects you get familiar in this first part of this lecture, I mean connected with these lasers and basics of the lasers. Every laser need to have something which is able to amplify the light. Yes, some gain media is necessary to produce the laser. So for the fibers and fiber amplifiers, we are basing on such a, let's say, phenomena and such a construction. Regarding the amplifiers, the optical amplifiers, they can be used typically in three different configurations. The most important and widely used, so-called inline amplifier. So it is just to optically regenerate the signal if we have extremely long fiber link. So after some certain distance, we need to just regenerate the signal. So we are adding amplifier in, let's say, chain spaced by long piece of a fiber. For example, it can be 100 kilometers or I don't know, maybe 500 kilometers even distance between the amplifiers. Yeah, so this allows to just extend the range of the transmission through the fiber, and you can see the whole thing, I mean the whole signal is optical here. We have no conversion to the electrical signal in any point of such a long link. Next application, which is in fact the best regarding the noise properties of the transmission line, is it is so-called booster amplifier. So we are just simply amplifying the light right after the transmitter. Yeah, regarding the signal to noise ratio in such a transmission line, the best approach is to boost a signal right after the transmitter. But of course there are some limits, so we cannot put, for example, too high power to the optical fiber after the booster, because we will excite some nonlinear effects. So we will have some losses, we will have some distortion of the signal. So the booster amplifier, of course, is quite useful, but cannot be used in the replacement of, let's say, inline amplifiers, for example. Yeah, because at the first approach, you can imagine we can amplify the light from the transmitter to 100 watts of optical power. Yeah. So after, let's say, 50 dB of attenuation, so we can calculate easily what will be the distance transmitted to the signal. So after 50 dB of attenuation, we'll have still 0 dBms of the signal. Yeah. So it will be quite useful for let's say the modulation for detection, but unfortunately, this 100 watt of optical power in the fiber will excite a lot of nonlinear effects, and in fact, it will be very fastly decreases to some nonlinear effect thresholds. Yeah, so we cannot use this approach quite widely. And the last possibility of the optical amplifiers, I mean the configuration, is the preamplifier. Preamplifier, we are just placing the optical amplifier right before the receiver. You can ask why this approach is better than, for example, using APD photodiode. You know the APD photodiode, it bases on this avalanche multiplication of the carriers created in PN junction, in this photodetection junction. Yeah, so we have also some gain, some amplification in the photodetector, but we can also use optical amplifier before such a detector, and it will be even better than using APD. The reason is exactly the same. Like I told you, the best is the booster. The principle is quite simple. The sooner you will place the amplifier in the transmission line, so you will have some gain in the transmission line, the lower noise figure of such a system you will have. Yeah, so in this case, this configuration will be better than using APD photodiode, and APD photodiode will be better than amplifier after optical detection. Yeah, so it works like that. So this is why sometimes we are using also these preamplifiers, I mean optical preamplifiers, before the photodetector. Not only just for improving the sensitivity of such a photodetector, but also to improve signal to noise ratio of the whole transmission line. So it also just enables to transmit the data through a longer distance, yeah, because the signal to noise ratio also is some limiting factor. And of course, regarding the optical amplifiers, we can have a lot of parameters which are characterizing such amplifier. Starting with the gain, of course. The gain defined quite simple as a ratio between output and input power. Of course, typically it is expressed in the decibels, in dBs. Gain efficiency, because optical amplifiers, of course, they need to be power supplied. Yeah, so we need to put some electrical power to such an amplifier, and we will have some optical power on the output. So gain efficiency tells you what will be the gain per each of the milliwatt of pumping power for such amplifier. Gain bandwidth tells you what wavelength range amplifier is able to amplify. You are making the erbium doped fiber amplifier exercise on the laboratory, so you know the noise spectra for such amplifier is pretty wide. Yeah, we can say from, let's say, 1520 nanometers up to 1580 or even more. Yeah, so this is the gain bandwidth of such amplifier, because the noise typically quite nicely match the gain spectra of such amplifier. Gain saturation, this is the phenomena you also see it on the laboratory. If we are putting the power to the amplifier, this transfer characteristic looks more or less like this. So the amplifier has some certain limit of the output power, yeah, P out max. And it is, of course, given by the efficiency of the amplifier and the pumping power for such amplifier. Yeah, so this gain saturation occurs for every amplifier, also for the optical amplifiers, and it just simply tells you what is the maximum output power for such amplifier. Sometimes for the applications with extremely high transmission rates, also polarization sensitivity and all the dispersions connected with this polarization can be important. So sometimes you can also meet polarization sensitivity for the amplifier. And the last thing connected with every optical amplifier, amplified spontaneous emission noise. Yeah, you know the phenomena of spontaneous emission, but in the fiber, since such optical amplifier is quite long, if we have some, let's say, ion emitting spontaneous photon, this photon, of course, is propagating through the fiber and can be amplified by this active fiber. So it creates and takes out the gain from the media. Yeah, so this is why there are limits, for example, for the gain for such amplifiers. Yeah, every spontaneous photon which is propagating in such a fiber can be amplified by the amplifier. So the power on the output of such amplifier, even without any signal, can be quite high because of this phenomena. Yeah? So we have no pure noise, pure spontaneous emission on this output of the amplifier, but we have so-called amplified spontaneous emission, because these emitted photons are amplified in the other parts of the fiber. And three main types of optical amplifiers you can meet. The most important regarding the telecommunication and also fiber lasers, these are rare earth doped optical fiber amplifiers. So we have just fiber which is doped with ions. These ions are just defining the wavelength of the pumping for such amplifier, and of course the wavelength of the amplification. The next part, there are Raman amplifiers, and Raman amplifiers are quite nice devices because they can be built basing on standard fibers. Even in standard single mode fiber, we can excite so-called Raman scattering, and this phenomena allows us to have also a gain at certain wavelength. I will show you something about these Raman amplifiers. And the last main type of these amplifiers are semiconductor amplifiers. You can imagine if we have semiconductor laser, yeah, more or less like this, PN junction, of course, here we have the gain media and the mirrors in the case of semiconductor laser. If we just remove a mirror from both sides and put here some anti-reflex coating on it, we can have a structure which is able to just simply amplify a light instead of generating a light like a laser. So these are the semiconductor amplifiers. Of course, every type of these amplifiers, they have their advantages and disadvantages. So there is a place for applications for every type you can see here. They are complementary to each other, in fact. And the possibilities, especially focusing on these rare earth doped fiber amplifiers, you know the erbium doped fiber amplifier. So we are doping with the erbium and operating around this third telecommunication window. Also, close to this third telecommunication window, we have thulium doped fiber amplifiers operating here. Regarding the laser technique, thulium is also able to operate from 1.9 up to 2.1 micrometer wavelength, so longer waves, more for scientific applications, not for the telecommunication, because the attenuation of a fiber is much higher for such a wavelength, and even slightly longer wavelengths from 2.0 up to 2.4, we have holmium doped fibers able to emit such a long wavelength. This type of lasers, I mean, basing on such active fibers, are quite useful for the medicine application, for example. Regarding the second telecommunication window, we have praseodymium doped fiber amplifiers, and they were developed when this second telecommunication window was in wide use. I mean, when the second telecommunication window was developed, but praseodymium doped fiber amplifiers, they have quite poor parameters. So right now it is some kind of blind alley of let's say optical fiber amplifiers, because as I told already, the parameters are poor, and in fact right now they are useless, because the whole telecommunication was just transferred to this third telecommunication window, where we have erbium doped fiber amplifier, which is way better than praseodymium doped fiber amplifier. And regarding fiber lasers, especially technological fiber lasers, I mean high power fiber lasers, we have these two dopants available, I mean ytterbium and neodymium doped fiber amplifiers. Neodymium is operating at 1.064 micrometers. I think you are familiar with this number, because also solid-state lasers doped with neodymium ions are operating at this certain wavelength, and ytterbium doped fiber, ytterbium dopant, which allows to make lasers from 1 micron up to 1.1 micron. Yeah, so pretty wide range of the wavelengths, and the biggest advantage of ytterbium doped fiber amplifiers for making fiber lasers is extreme high efficiency of such amplifiers and lasers. Much better than neodymium, and other types also cannot even be close to the efficiency. I mean, optical to optical, the pumping power versus the output power from such a fiber laser, for example, we can have even 19% of the efficiency for such a structure. Okay, I think showing you these high power applications of the fibers, especially high power fiber amplifiers and the lasers, I will show you why this ytterbium is so nice and has such a high efficiency. Yeah, so some basics of, I hope you remember these basics. We can have different, of course, phenomena which can appear in the media, which is doped with, let's say, erbium ions or different ions, but doped with some atoms or elements which has some certain discrete energy levels. Yeah, we can absorb a photon when we have something in basic state, the lowest energy level. Forcing it to be in higher energy level, of course, is connected with the absorption of the photon. If we have some excited atom or ion, after some certain time, it will go to the basic state, emitting spontaneous photon. So the direction, the phase, the polarization of such a photon, of course, is let's say random. and we can have also this stimulated emission, which is the basis for optical amplification, for optical gain, because this emitted photon is exactly identical with the photon which just stimulates this emission. Yeah, so this is why this phenomena can act like an amplification, like an gain, because on the output we have two identical photons which are adding to each other, to the field, to the electromagnetic wave. In fact, the real systems, real lasers, I think you know it, they need to have at least 3-level system to operate, to be able to have this so-called population inversion. It means more atoms or ions are in this second stage than in this basic ground stage. So we have typical schematic of operation for such a system. Pumping is from this basic level to this upper pumping level. So these photons they have much higher energy than the photons which are emitted here, yeah, because the energy of the photon, of course, is defined by the energy difference between the levels. So you can see why, for example, we are pumping erbium doped fiber amplifier at 980 nanometers, because this is the wavelength which can be absorbed and give this transition, yeah. And the photons are emitted and gain we have at 1550 nanometers wavelength, yeah, because this level, of course, this transition has lower energy. You remember the energy of one single photon is defined by h ni, where h is the Planck constant and ni is the frequency of this signal. Of course, ni is equal to c over lambda. So you can tell the longer wavelength, the lowest frequency, lowest energy, of course. Yeah, so this is how it works. Spontaneous emission, and here you have the energy diagram for this, let's say, the most important type of the amplifier regarding fiber telecommunication. For erbium doped fiber amplifier, these are the energy levels of the erbium ions in a glass. So you can see every possible wavelength which can be absorbed by such a active fiber, starting from 410 nanometers and ending at 1.48 micrometer wavelength. Somewhere here, yeah, you can see also this 980 nanometer wavelength. For pumping, of course, pumping at different wavelengths will excite the erbium ions to higher energy levels, but the emission we are using for making and for operating with this erbium doped fiber amplifier is between these two energy levels. So you can see by default why we don't want to use, for example, pumping at such a short wavelength, because we are pumping to this energy level and then we are wasting huge amount of the energy here. So the efficiency of such a pumping will be extremely low, for example, yeah. It also can lead to emission at different wavelengths. You can see you can emit red radiation, some blue radiation, green, and other wavelength. Of course, it will be also waste of the energy, because you have no guarantee that from this level it will go to this, let's say, upper level needed for our stimulated emission. It can go to other energy level, so the energy will be just wasted, because then it can go to the basic state like this. Yeah, the possible transitions, there is a lot of possibilities, and of course a lot of possibilities to weight and energy. So the wavelength which is typically used for pumping erbium doped fiber amplifier, this is the 980 nanometer. The pumping at this certain wavelength is the best one for pumping erbium doped fiber amplifier. Also, some other phenomena is making some losses in the some in this pumping scheme, so-called excited state absorption. Yeah, one pumping photon can excite erbium ions to this excited state, and then this ion can absorb another pumping photon. It is possible more or less for this level. Yeah, so we are exciting the erbium ions to this level, and then it is able to absorb another photon and excite it to this certain level. You have this marked, this ESA, excited state absorption, and then after absorbing 2 photons, this erbium ion will go to the basic state, emitting green radiation. On the laboratory, you can observe this green radiation if you have this erbium doped fiber amplifier, and if you look closer to this active fiber, you will see it just simply emits a green light from the side of this active fiber. If you want to see it, let's say, in better way, just ask me. We will switch off the light in the laboratory for a moment, so then you will be able to see quite nice green radiation going out from such a fiber. Yeah, of course, it is night visible radiation, but looking at this fact, it is wasting the energy of this pumping radiation. So regarding the operation of amplifier, of course, it isn't good phenomena allowing to operate the amplifier. It just decreased the efficiency of the amplifier. And for erbium doped fiber amplifier, we have this basic, let's say, scheme of the pumping of the operation, but also additional scheme. Let's say you can tell it is 2-level diagram, but in fact, if you put some ions in a glass, not have them in the air, every level of this erbium is splitted in many sub-levels due to different quantum mechanisms. They are appearing if you just put some ions or atoms in some solid state, for example the glass, which has some let's say structure of these particles inside of a glass. Yeah, so it just makes the let's say single energy level for one single erbium ion. In fact, it is changed in white energy bands for such a material. Yeah, and you can see we can just simply pump from the bottom state of these levels to the upper state of this band. Yeah, so we are pumping in such a way, and of course gain is possible for transition like this. Yeah, this bands, these white absorption and emission bands are quite helpful, in fact, because they are making the gain bandwidth for such a amplifier to be extremely wide. Yeah, I draw you the picture previously. The bandwidth of erbium doped fiber amplifier can be from 1520 up to 1580 nanometers, or even more for some special configurations of the amplifier. It is possible to have the gain even up to 16, let's say 20 nanometers. So for even for such a high wavelength, yeah, we will use then transitions from this range. We can also build an amplifier. And typical structures, you are getting familiar with them on the laboratory. You are investigating, in fact, the characteristic of the amplifier for, let's say, every of these 3 configurations. And here you have main differences between the 3. Co-propagating pumping is at first used if you want to have low noise applications, so as a preamplifier. Counter propagation pumping we are using typically if we are building the booster amplifier, and to have some, yeah, because this one is the best regarding the output power. This one is the best regarding the noise properties. And if you want to have some compromise between these two, you can use bidirectional pumping, and you can also tell this configuration will be the better for inline amplifiers. Yeah. So that's all. Yeah, this configuration also has the highest gain. Highest output power, it isn't the true, in fact, because this highest output power on the laboratory, for example, is given by pumping the amplifier with two pumps instead of single pump. But if we will use for bidirectional pumping two pumps, but with half of this pumping power of one single pump in these other two configuration, you will have output power exactly in the middle between counter and co-propagation configurations. Yeah, so this one, it isn't that true. In fact, of course, in real applications where the pumping power, the maximum pumping power, this is the limit connected with this maximum power of one single semiconductor laser, because this is the limit, in fact, for such erbium to fiber amplifiers. We cannot build. There are some technological limits. We cannot build a semiconductor laser pigtailed into single mode fiber with power you want to have. I mean, there are some limits to the maximum power of such a laser. Yeah, so if you just build the configuration regarding this maximum power, this bidirectional pumping, since we can use two pumping lasers instead of one, it will be much better regarding also the output power. And the gain characteristics I told you previously, typically we are using, for example, for this range of the wavelengths, yeah, regarding the gain, it should be more or less constant in the band we are using, but you can see it is possible to have a gain even at 1.6 micron or even slightly longer wavelength. Yeah, so this is of course possible to build such an amplifier, but this amplifier cannot be need to be optimized for the longer wave operation. It should have much longer active fiber, and if we are building the amplifier for such a range of the wavelength, this wavelength need to be attenuated, otherwise they will dominate the whole gain spectra of such amplifier, and we will have nothing to gain here. I mean, no energy left for have a gain on 1.6 micron. And of course, there are amplifiers which are able to operate in such a wide band, but they are basing on two parallel amplifier. One of them is at this, let's say, C band. This C and L bands are taken from this telecommunication names. This whole third telecommunication window is divided into different bands. S, this is short, C, central, L, long, and right now also ultra long appears above this 1.6 micron wavelength. Also for these longer wavelengths, some channels and amplifiers are produced and used, of course. Yeah, but if you want to have a wideband amplifier, in fact, you need to have two of them. Just signal is splitted regarding the wavelength, so we are just separating the bands here using some band pass splitter and then connect it together into one fiber. Okay, something connected with the noise of the amplifier. I told you already it is called amplified spontaneous emission because it isn't pure spontaneous emission, but it can be amplified, and you can see this amplified spontaneous emission is propagating in both directions in such active fibers. Yeah, they can be propagated in opposite direction to the signal and in the same direction. Of course, regarding the amplification of the signal, only this noise is adding to our signal. This one is backly propagating, so we can just simply put the isolator here. You are familiar with this device, and block all these, let's say, backwardly propagating noise using this this isolator here in the input of our amplifier. Yeah, so it works more or less like that. Yeah, something additional informations about this spontaneous emission, and this noise is the main source of the noise in the erbium doped fiber amplifier, because you can imagine there are also different types of the noises connected with some shot noise of the carriers, photons in that case. Other factors, for example, the noise of the photodetector, because we need to just consider the noise as a noise of the whole system. Yeah, so in such a systems, this amplified spontaneous emission noise is the main source of the noise of such amplifier. And here you can see the typical spectra of a noise. Sorry for that. Here I just gave you moc pompy. Moc pompy is the pumping power for the amplifier. It was the amplifier I just was investigating in my PhD thesis long time ago. And these are the noise properties of such amplifier. You can see the spectra of this noise is quite similar. I mean, the shape is quite similar to the gain spectra of such amplifier. Yeah. So observing the noise spectra of the amplifier, you can also tell more or less, of course, what will be the gain bandwidth of such amplifier. And the most important parameter regarding these noises, these are optical signals to noise ratio. You can see it on the spectrum analyzer when we have this optical noise and you have this signal. So measuring the distance between the peak of the signal and the noise floor, you can determine this optical signal to noise ratio for such amplifier. And then it just simply calculates to the noises on the photodetector. As you can see, there are 5 different sources, because the noise can also interfere with the noise and create some photodetection signal. The signal can just interfere with this noise. Also, between bandwidth, the noise appears, but it isn't so important. As you can see, in well-defined erbium doped fiber amplifier, I mean well-designed erbium doped fiber amplifier, signal to optical noise beating signal is dominating in the noise on the photodetector. Regarding the photodetector, the beating means the interference. Yeah, we have a signal at one certain wavelength and we have a noise at some range close to this wavelength of the signal, and these two signals are interfering, changing into some signal, some electrical signal, producing a noise on the electrical side. It works more or less like this. Yeah. So typical parameters of such erbium doped fiber amplifiers: the bandwidth, as I told you previously, different bands, C band, L band. For S band, typically thulium doped fiber amplifiers are used, or semiconductor amplifiers also. Typical gain is somewhere between 20 up to 30 dB. Yes, this is typical value, especially if you want to just build the amplifier only for this, let's say, top gain wavelength. It is around 15-30 nanometers. Yeah, so for this certain wavelength, it can be even 40 dB if you just design the amplifier properly and you want to have the gain only at this certain wavelength. So it can be even 40 dB. 40 dB, just to remind you, this calculation is connected with these dBs. 40 dB means 10 to the power of the 4th, so 10,000 times. This is the amplification gain of such amplifier. And typically 30 dB is 1000 times. This is the gain of such amplifier, so pretty high. Yeah, regarding the electrical amplifier, for example, it would be the amplifier which has gain 60 dB, because in electrical amplifiers typically we are giving the gain in, let's say, voltage to voltage values. So it means we have 20 logarithms to calculate. So 1000 times it will be 60 dB, not 30, because here we are speaking about the power gain. Yeah, we are calculating the power gain. So this is why we are using this 10 logarithms of the relation between output and input power. So it means 30 dB is 10 to the power of a 3. Typical output power in the saturation, of course, 10 up to 15 dBms, but of course it is possible also to have higher gain, higher output power, pumping with the higher pumping lasers, higher power pumping lasers. Right now it is quite possible to have even couple watts of output power in single mode fiber. It is also important, yeah. But using different structure of the fibers, I will tell you more about it on the next lecture. I mean about the high power amplifiers. And the parameter which just tells you about the noise properties. Of course, we have this optical signal to noise ratio and other parameters, but the most important and telling, in fact, the most is so-called noise figure. Noise figure just simply tells you how much signal to noise ratio will be degraded after amplification. So typical noise figure for erbium doped fiber amplifiers is somewhere between 4 and 6 dBs. And theoretical limit for erbium doped fiber amplifier is 3 dB. 3 dB is the theoretical limit for optical amplifier. It cannot be less than 3 dB. Yeah, because of the nature, in fact. Nature just gives us such a value. It is quite close to the quantum mechanisms of this gain, because you remember, we can create additional photon by this stimulated emission. Yeah. So we will have 2 photons, but the probability of the stimulated emission is 50%, and other 50% is the same probability is to have some spontaneous emission instead of this stimulated. Yeah. So you can see every photon has 50% of the probability that it creates another photon and will be gain, and 50% of the probability that we will have on the output 2 photons but not synchronized with each other. So in fact we will have a noise. So this is why we are degrading the signal to noise ratio. At least 3 dB means twice, yeah, 2 times less we will have as a result of this amplification. And regarding these pictures I showed you already, of course, I was speaking about these erbium doped fiber amplifiers, but almost all the things you saw, they can be also applied to holmium, thulium, neodymium, ytterbium doped fiber amplifiers. All of them, of course, the parameters, they will be different, especially the wavelengths are different, but also the possible gains and other factors. But the principle of operation and of course also these configurations are pretty the same. So right now we can go to the second type of these optical amplifiers, Raman amplifiers. And Raman amplifier is basing on this Raman effect. This is non-linear effect, which is quite hard to, let's say, fully explain, especially in the scope of this lecture. But you can imagine that every particle of our glass is vibrating. Yeah, every particle of a glass is vibrating. So if a photon hits such a vibrating particle of a glass, if it hits, depending on the phase, I mean, if the photon just hits into the particle which is moving in the same direction, of course, as a result, the energy of this photon will be slightly smaller. Yeah, this resulting photon will have slightly smaller energy because, you know, some quantum effects and other things, it is of course possible to calculate, but the energy will be transferred to this movement of the particle. Yeah, if such a photon just hits to the particle which is moving in opposite direction, of course it can be just reflected, and the energy of such a photon will be higher by this energy of this movement of this particle. Yeah, so we have the mechanism when we can just slightly change the wavelength of the photons because of this phenomena, and additionally this additional energy, artificial in fact, creates artificial energy level in such a media, allowing us to also have some stimulated emission in such a media. Yeah, it is quite complex, but here this dashed line means more or less this artificial energy state, and you can see we can transfer the energy from higher energy photons into lower energy photons. Yeah, because of this phenomena. So we can obtain a gain in such a material, and in fact this phenomena appears for every possible material, even for a glass. Yeah, so since we have an optical fiber made of glass, a lone fiber can utilize such a phenomena to create some gain. This gain will be at longer wavelengths, the lower frequencies than, let's say, our pumping signal. For silica glass, this shift is typically 13 terahertz. Yeah, so it means if you recalculate it to the wavelength, if you just to such a fiber, if you launch a light at the wavelength 1.45 micron, for example, and the energy, I mean the power of such a pump will be high enough to exceed the threshold of this Raman scattering, you can build an amplifier which will be able to amplify a wavelength 1.55 microns. Yeah, so you can create, in fact, an amplifier using this phenomena, and the wavelength which will be amplified is defined by this pumping wavelength and this frequency shift due to this Raman scattering effect. Yeah, so we can create amplifiers using pure fiber. So we can build, of course, this Raman amplifier in two ways, or as a discrete pumped Raman amplifier. So we are using some fiber because, you know, this Raman threshold and efficiency of this process is quite low, but we can create fibers which have much higher Raman scattering coefficients. So we can just create special Raman fiber for such a purpose and just build a Raman amplifier in more or less the same way like we are building erbium doped fiber amplifier, for example. But we can also build so-called distributed Raman amplifier. You can imagine if we have long transmission line, for example 100 kilometers, this Raman scattering in such a long fiber will be high enough to just simply use this fiber, our transmission line, as a gain media. The only thing we need to do is to just put some pumping radiation through our transmission media. Yeah, so we have our transmitter somewhere, then we have long path of the fiber, and we have our receiver, and we are just putting pumping light somewhere here from the receiver side, and we are creating distributed amplifier because the gain is distributed along the fiber here, along our transmission line. Yeah, so you can tell it is the holy grail of optical telecommunication, because we can create optical amplifiers for free. They can operate at various wavelength defined only by the pumping wavelength. Yeah, so it should be the gold solution for the optical telecommunication. Unfortunately, these Raman amplifiers, they have also some disadvantages, in fact quite significant. I will tell you in a moment, but at first I will show you typical application. As you can see, typical application of such a Raman amplifiers are connected with erbium doped fiber amplifier. They allow us to just increase the distance between these inline amplifiers, let's say these standard inline amplifiers. Yeah, if we are transmitting some information through the fiber, we are limited from the both sides. I mean, the low signal, the signal transmitted in the fiber can be lower than some threshold value defined by noises in our system, and the maximum signal power is defined by nonlinear effects which can appear to the signal if it has just too high power. So our signal, the power of our signal must be all the time kept between these two, let's say, margins. Yeah. So if we have such a margins and we have some losses of our fiber, maybe I will change the color of my pen to this one. Yeah. So the power is dropping in the transmission line, and here in this point we should put the amplifier, the erbium doped fiber amplifier, to gain a signal up to the level of this maximum possible, and then of course next span, next segment of our network, and increase another gain station, and so on. Yeah, so it should be like this. Yeah, so the distance between each consecutive amplifier will be as follows. If we just simply use this Raman amplification, we can design our transmission line exactly according to this picture. You can see the power level is decreasing, but this Raman pumping, of course, it is absorbed in this fiber. At some certain distance, the Raman gains start to appear and the signal level will increase. So in our station we need to just simply increase the power level to this maximum value, and then we have another span and the power will be acting like this. Yeah, so at some certain level, so it is this minimum power level, of course, cannot be lower than noise's limit of the transmission. Yeah, but we, using this approach, this additional Raman pump, which is just introduced to our transmission line, allows to increase the distance between these optical amplifiers, these inline amplifiers. And typically, regarding these things I told you, we are pumping such a Raman amplifier using these different wavelengths to have wide bandwidth of the gain. Yeah, because the gain is defined by, I mean, the wavelength of the gain, of course, is defined by the wavelength of the pumping, because this shift between these pumping photons and amplified photons is constant for certain type of a fiber. So pumping configuration for such amplifier is pretty complicated. You can see typically couple different wavelengths are used at different powers just to have the spectra, the gain spectra of such a Raman amplifier more or less flat. And you can imagine this will be much more costful, I mean produce much more costs for the application than one single erbium doped fiber amplifier, because the gain of such amplifier, such a Raman amplifier, you have here the gain typically 13 dB. Yeah, so we cannot replace these erbium doped fiber amplifiers with these Raman amplifiers, but they can be used as some, let's say, help, allowing to increase the distance between these amplification stations. And this is typical applications of such a Raman amplifiers. Additionally, using these Raman amplifiers, we can meet couple different limits and not nice phenomena. Noise is pretty complicated in the Raman amplifier, so proper designing of such amplifiers and sensitivity to the signal level, to the gain level, and other factors are pretty complex and making the operation of such amplifier quite hard, especially if the conditions are changing. But also we can have fast response time of a gain. Yeah. You remember the characteristic of the amplifier, this transfer characteristic, I mean P out versus P in. Yeah, and we have some saturation here. It means if we have a gain characteristic for such amplifier, it will be low for low input, high for low input powers, and at one certain P in, it will start to drop. Yeah? Typically, we are operating somewhere here. It means changing the input power will change the gain of the whole setup. Yeah? But because typically we are operating at the signals which are consisted of a lot of wavelength, because the Raman amplifiers typically are used for modern WDM telecommunication. I mean, we are transmitting a lot of channels simultaneously at different wavelengths. So what will happen if we just simply change the energy, I mean the power, in one single channel? The total power of course will change, so the gain for the whole amplifier also will change. And for erbium doped fiber amplifier, it isn't huge problem, because the response of the gain, I mean time of a response, is typically couple milliseconds. Yeah, so if we just simply remove a channel or add a channel, the gain will slowly change for whole amplifier, but every signal in fact is zeros and ones. Yeah, so quite rapid change of this optical power transmitted in every wavelength. They are appearing and disappearing with the high frequency, strictly speaking, in fact. Yeah, so for erbium doped fiber amplifier, it isn't sensitive for the rapid power changes. Unfortunately, Raman amplifier, its response time for fastly changing the amplitude of the signal, so for the transmission, in fact, yeah, we are transmitting zeros and one, this response is pretty fast. It means even 0 and 1 transmitted can slightly modulate the gain. It means we are modulating a gain of our amplifier by the signal itself. So it will lead to some crosstalks to another channel. Yeah, if the channel, for example, is transmitting constant value, and we are slightly changing the gain of this amplifier, we will change the level on the output, even without any input signal modulation. And of course, if it is modulated, it will be also additionally modulated by these consecutive channels. Every channel will lead to crosstalks to other channels because of this cross gain modulation. Yeah, so they aren't able to operate with the systems with low transmission rates. Quite weird, but for extremely high transmission rates, these Raman amplifiers, they will be okay, because this response time will be too long, yeah, to respond for 1 bit of transmitted signal. But for low frequency signals, Raman amplifiers are useless. Okay. Also, as a disadvantage, very high pump power requirement. We need to have high power semiconductor lasers to pump such amplifiers. you can imagine to just excite this Raman scattering. So high power means we need to have special components for some certain power levels. You can just make the price for such a component even be 10 times higher or even more. And of course, these high power components, they are also sensitive to some, let's say, damage and other things connected with this Raman gain. Typical behavior is if something's wrong goes with these Raman amplifiers. In fact, every element, I mean passive and active element in transmission line close to this Raman amplifier, they are destroyed by this high energy pulse, because typically if something's wrong goes with these Raman amplifiers, it starts to emit some pulses, and the pulses are huge energy, so they are destroying they can even destroy connectors, for example. Yeah, so burn a hole in a core of a fiber in such a connector. Okay, and last, amplifiers for fiber telecommunication, not only for fiber telecommunication. As I told you already, if you just take out the mirrors from semiconductor laser and put some anti-reflection coating instead of these mirrors, you will have something which is able to just amplify a light. So just simply connect a fiber, align a fiber not only from this output side, but also input side of such a structure, and you will have something which is called semiconductor amplifier, or SOA, BOA, LOA. SOA is odd semiconductor optical amplifier, BOA is odd booster optical amplifier, and LOA is for linear optical amplifier. Boosters are typically used as a name tells everything, in fact, because you can have a transmitter and then semiconductor amplifier with high saturated output power just to boost a signal into the transmission line. You can see also typical case for such amplifiers, and it is in fact exactly the same like for telecommunications semiconductor lasers. Also typical butterfly package, typically 14 pins, and the only difference is this second fiber connected with this second side of such a structure. If you just remove this part, this is how typical semiconductor laser for the telecommunication looks like. The pumping lasers and also signal lasers are more or less looking like that, and typical case this butterfly, because inside of such a structure we have also this thermoelectric cooler, some temperature sensor, and also photodetector, so just to provide the possibility of this temperature stabilization and other things needed for proper operation of such devices. Of course, some technological let's say issues connected with this construction, different designs for different applications, not so important. The important are the characteristics of such amplifier. Here you have typical gain versus optical output. Yeah, so you can see for some range of the optical output will have the saturation, so gain start to drop, and this is typical parameter for such amplifier. This saturated output power defined for this point where this output power, no, it is for this point where the gain drops by 3 dB. And this is saturated output power. For this case, it will be 14 dBms. Also, the wavelength dependence, you can see they can operate at quite wide wavelength range, and typical gain is 20 something dBs. Yeah, so lower than for erbium doped fiber amplifier, but not so low. So they can be quite useful also like preamplifiers regarding this gain. And you can see changing the current, of course, for such a semiconductor amplifier. We are changing the gain and slightly changing also these spectral properties. So nothing else I should add to this, only these advantages and disadvantages. Advantage, exactly the same like for semiconductor lasers. In fact, we can have the wavelength of operation of such amplifier. It is defined by the type of the semiconductor, yeah, the composition of this semiconductor, because typically these are the semiconductors from this A3B5 group, where the composition, the proportions between the elements in this semiconductor defines as this band gap energy, and also defines the wavelength of the operation for such amplifier. They have compact structure, yeah, because they have pretty small, like semiconductor amplifier. Nice feature, they are electrically pumped, so we don't need to use additional lasers to pump such a structure, because doped amplifiers and these Raman amplifiers, they are using optical pumping, yeah, so we need to use additional laser as a pumping source. Here we are just driving by a current flowing through this PN junction. So it is also connected low power consumption and also quite high efficiency for such amplifiers. Disadvantages: low output power. Yeah, these are the lowest output power amplifiers possible, because erbium doped fiber amplifiers, I mean these rare earth doped fibers amplifiers, and also the Raman amplifiers, they can have much higher saturated output energy than 10 dBms. They can have even watts, or for some special applications even kilowatts of output power. Also, not so nice feature, high noise figure. High noise figure is given for such amplifier because of this coupling efficiency. Yeah? If we are just putting the light from this input fiber to the semiconductor structure, we have quite high losses here. And every loss before amplifier increase noise figure of such amplifier quite significantly. Yeah? So this is why the noise figure for such amplifiers is quite high. Because of the nature, it is some, let's say, planar waveguide in such an amplifier, planar structure. Yeah? It doesn't have a round symmetry like for our standard cylindrical fibers, but the symmetry of this waveguide, which is the base of such amplifier, is, let's say, linear. Yeah, so the mode field for such a structure is not Gaussian, but sometimes differ a lot from the Gaussian shape. So it means we will have quite high coupling losses from the Gaussian shape mode in standard fiber into such a mode field in this planar fiber of this amplifier. So the losses are high. And also polarization dependent gain because of the nature, once again. Yeah, the direction of the current flow also determines the gain, and the gain is different for the vertical and horizontal polarization in such a structure. So we'll have a gain. In fact, it can be quite huge difference between the gain for horizontal polarization and vertical polarization. It can be even couple dB of the difference for such a structure. So the polarization control is needed. So this is why typically they are used as a booster amplifiers, because they are coupled directly to the laser. And of course, if they are coupled to the laser also has some certain defined polarization, so we don't need to take care about the polarization. If you put somewhere else the amplifier and you don't have some polarization controllers, or you don't use these PM fibers, these polarization maintaining fibers, you will have these issues connected with the gain changing with the polarization of the light transmitted. And also the same like for like for these Raman amplifiers, fast response time of a gain. Fast response time of a gain. Fortunately for this type of amplifiers, this response time is slower, but it just limits such amplifiers to be used at least for, let's say, 2 or 3 gigahertz systems. For lowers transmission rates, we will have quite huge response of a gain with these zeros and ones. Yeah, so it will act for one single channel as a compression, because zeros, they will be amplified more than the ones. Yeah, one will saturate the gain, zero will operate at this high gain point. So you can imagine it will act like a compression for the signal. Okay, and regarding the amplifiers, I think we can just finish. So you know already all the elements needed to build telecommunication system, not only telecommunication, also fiber lasers, you know, the transmitters, receivers, all the passive elements, also amplifiers. So right now we can just go to the, let's say, roots and the main reason of the fibers and development of the fibers. Do you remember what was the main reason of the fibers development? This word was appearing all the time today. Of course, the telecommunication. Yeah, so telecommunication, this is the main reason why the fibers were developed. And just to remind, carrier frequency for optical waves is extremely high. Optical waves, they have hundreds of terahertz in frequency, so the wide band of such a waves allows us to pack a lot of information for such a waves, because it is connected together. Small attenuation of optical fibers makes also them ideal as an ideal media to transmit the signals. 0.2 dBs per kilometer, yeah, typically, or even less. It means 100 kilometers of the transmission will give us 20 dB of attenuation. So if we have the transmitter at 10 dBms optical power, on the receiver side we will have minus 10 dBms. It is way well enough to fully detect, demodulate signal even in extremely high transmission rate, and the bit error rate in fact to be error free, less than 10 to the minus 9. This is the condition to consider the transmission to be bit error free. If the bit error rate is less than 10 to the minus 9, it means every billion, for 1 billion bit transmitted, one of them can be transmitted wrongly with some errors, or less, of course. Also, right now, this all optical signal regeneration erbium dot fiber amplifiers can be applied. And another thing, transparent optical networks, modern approach to the network. We are transmitting the signal from the transmitter up to the receiver without any conversion to the electrical signal somewhere on the optical path. Yeah, so the photon which is just transmitted from the transmitter just received is receiving receiver or its child's of this photon as a result of the optical amplification or something like that. But we have no change from the photon into electron in any part of this transparent optical network. Just to remind you also, this first, second, and third telecommunication windows, the idea behind them was developing of the laser sources and also developing the purity and the quality technology of fabrication of the fibers. Yeah, so you can see right? At first there was first window, second window was operating for quite a long time, so a lot of in fact billions of kilometers of fibers was applied in such a, let's say, applications. I mean, for this second telecommunication window. Right now all the things are moving to this third telecommunication window, also using this second window fibers, I mean the standard single mode fibers, because you know already how to deal with this dispersion which appears at 1.5 micron and this standard single mode fibers. Yeah, the capacity of the fibers, of course, I mean the information capacity of the fibers, are given by the bandwidth. So you can see for the third telecommunication window we have quite huge bandwidth available, starting from 1.45 micron, ending somewhere close to 1.62 micron. So if you just recalculate it using this certain formula, if you want to recalculate it from this bandwidth expressed in the wavelength into the bandwidth expressed in the Hertz domain, in frequency domain, you need to use such a formula. It is just simple, the derivative of this simple formula if you are calculating from the wavelength into the optical frequency. Yeah, but calculating the deltas, you cannot put delta in the denominator of this fraction. So this is why we are using derivative and calculate it using this certain formula. And of course, there are some limits. So the whole history and development of such a let's say systems faced with some limits and other things. The main limits until now is the speed of the electronics, yeah, so the speed of the modulators and other things, and fiber losses, but connected mostly with these nonlinear effects right now. How to increase the capacity of the fiber? I mean, how to increase the amount of the information we want to we are able to transmit. So the first approach, quite widely used for the first and the second telecommunication window, was optical time division multiplexing. So we had 3 optical transmission channels, and they were multiplexed in time domain. So we need to have some device which is able to fastly change the connection from one channel, second, third, and so on. And of course, it is all the time repeating. So we are transmitting the information for every channel in so-called time slots. Yeah, so every channel has its own time slot. Then at the receiver side, we need to at first just recover the clock for this multiplexation, yeah, and the multiplex, of course, the signal. But you can see, in fact, we are limited with this multiplexers capability to fastly change the signal source. So this approach changes quite fastly into approach quite well known, in fact, from, let's say, standard radio technique. Yeah, optical time domain multiplexing is limited by the electronic bandwidth, so we can change the approach, and we can use the approach possible and utilize for the standard radio transmission. Here you have something which I just took a couple years ago. This is electrical spectrum analyzer, which shows you the electromagnetical waves from the 88 megahertz up to 108 megahertz frequency. What are these frequencies? What is the range of these frequencies? Can anybody just tell me what are these frequencies means?
The FM radio?
Exactly, yeah. So here you can see different peaks, Every peak, of course, is transmitted at different frequency. You know it, tuning the radio for some certain station, you need to just tune to this peak, yeah? And then you can receive the information transmitted with this certain frequency, this certain peak. But one thing here, it isn't visible. I mean, the bandwidth taken by such a channel, yeah? Because observing and at the first approach, you can tell you can put as many frequencies here as possible. Unfortunately, every transmission is connected with some bandwidth taken, and for example, for FM transmission for radio, typical channel size here, I mean the bandwidth of the channel is 150 kilohertz. Yeah, so this is the bandwidth taken. It is directly from the modulation of the signal and the bandwidth of the acoustical signal, which is modulating our carrier. Yeah, so if we have some carrier frequency and we start to modulate it, in fact, this frequency changes into some bandwidth taken by a channel. It means we cannot put the channels too close together, because then we will have some crosstalk between the channels. So we need to have some certain spacing, yeah? The more information we want to just transmit through such a media, we need to have wider bandwidth taken. And for example, if you want to see right now there is a digital TV signal transmitted, yeah, so it is completely different story, but for the analog TV, which was popular not so long ago, let's say 20 years ago, only analog television signals, they were transmitted, broadcasted and received, of course. TV signal, for this standard definition, it is something close to 640 by 480 pixels. So you can imagine this was the standard for the television, this analog television. Yeah, the resolution of the picture, more or less. The TV channel took 8 megahertz of the bandwidth. Yeah, so in fact, if we want to transmit the TV channels through this bandwidth for this FM radio, we would take almost half of it. So you can see, the more you can imagine, the TV signal is much more complex, and it carries a lot of more information than single audio signal only. Yeah, and of course, increasing the amount of the information we want to transmit, we need to have also the bigger bandwidth. So you can see why these optical signals are ideal, in fact, for transmitting huge amount of the information, because we have the channels which are operating at the optical waves, different wavelengths. Yeah, we can just make something similar to our broadcasting approach into the optical domain. We can just simply transmit different channels at the different wavelengths. Yeah, if we just simply modulate one single channel by some information, of course, we will take some bandwidth, but since here we have 100 terahertz, even if the bandwidth of our signal is taking, let's say, 100 gigahertz, we can pack a lot of channels in such a transmission media, and using different wavelengths, of course. So, starting of this approach, of course, is called WDM, wavelength division multiplexing. For let's say radio technique, it is called FDM, frequency division multiplexing. For optical waves, we are rather using wavelength than frequency of the signal, so this is why it is named wavelength division multiplexing. But in fact, it is exactly the same. Yeah. So you can imagine extremely simple WDM system can just simply use the signals transmitting simultaneously at these two wavelengths, this second and third telecommunication window. Of course, the application of this WDM system was made even before appearance of this third telecommunication window, and as a standard was so-called CWDM, coarse WDM system. Yeah, channel spacing can be 20 nanometers. So we can have a lot of, maybe not a lot of these channels. The amount of the channel is up to 18 channels. Yeah, spacing between channels given by this 20 nanometer is 3.5 terahertz. So we have quite distant channels, and of course we are wasting in this CWDM system, we are wasting a lot of bandwidth between channels. But this CWDM system has of course some advantages. The first and main advantage, they aren't so wavelength sensitive, so we don't need to stabilize the laser wavelength precisely, because it can tune with the temperature even couple nanometer to the left and right. And of course the quality of this optical filtering just for separation of the channels, yeah, we need to be able to optically separate the channels, yeah, to distinguish two different wavelengths. Yeah, so since they are spaced by 20 nanometers, the optical filtering is also extremely easy, in fact. Yeah, so this is why at some certain development stage these CWDM systems were used, and in fact they are still useful for, let's say some metro, for example, networks or something like that, for these short range networks, optical networks, where the amount of the channels, it isn't key factor. We want to only just transmit couple channels, but we want to have also cheap sources, cheap equipment, cheap filters, and other things. But modern telecommunication, of course, is basing on, let's say, much more dense channel spacing. Much more dense means here you have some, let's say, something taken from ITU standard, which tells you what are the normalized channel spacings and amount of the channels. And you can see the channel spacing is given typically in gigahertz, yeah, because the numbers are so small regarding the wavelength that the channel spacing typically is given in gigahertz. For 1.5 micron wavelength, so this is for third telecommunication window, this 100 gigahertz is equal to 0.8 nanometer of a distance spacing between the channels. If you want to have even lower channel spacing, to put more channels between each other, we will have 0.1 nanometer of the channel spacing. But in fact, from the practical point of view, only these two plays important role, especially right now, because look, we are closing channels together, and right now we are at the limits. If we have 100 gigahertz channel bandwidth, channel spacing, it means the bandwidth of our signal, especially regarding some margin, we need to have some spacing between the channel. The bandwidth of such a signal cannot be greater than 80 gigahertz. Yeah, the bandwidth of such a signal. It means the modulation frequency cannot be higher than 40 gigabits per second. Otherwise, we will increase the bandwidth taken by a channel, and we will start to having crosstalks. Yeah, so you can see, if we go for 50 gigahertz channel spacing, we will be limited to 20 gigabits per second. The transmission rate for such a system, yeah? And right now we need to just balance between the cost of the electronics for higher bit rates and cost of the optics for lower channel spacing. Yeah, so right now, somewhere here for this 50, there is a balance between the price of the electronics and price of the optics, because you can imagine if we have the 0.4 nanometer channel spacing, we need to extremely precise keep the laser wavelength constant and also extremely precise filter the channel of other channels. I showed you these Bragg gratings on the previous lecture, yeah, when I was talking about these passive fiber components. Yeah, so Bragg grating, of course, this is the device which is able to just separate one certain wavelength, but it has also some spectral properties, some lobes here. Yeah, so to precisely let's say separate signal which has the bandwidth 0.1 nanometer, and to avoid some crosstalks and other things, also the temperature of every element in such a system to separate, I mean, filters and other things, they need to be also precisely controlled. The price for such a narrow band element also will be much greater, and so on. So this is some, let's say, some compromise between the channel spacing, yeah, and the prices. And from one side we have these electronic prices going up with this frequency, and from other side we have optical components prices going up if we are decreasing the channel spacing. But you can tell and you can see we are in fact utilizing, just to summarize today's lecture, in fact, we are utilizing, in fact, the whole bandwidth of this third telecommunication window, yeah, without any space left between every channel. Yeah, we are able to do so. Oh, I just accidentally finished my presentation, so it is good point. So it is also a good time to ask if you have any questions, because as I told you, for today it will be enough. And if you have any questions, of course, I can explain something more. If not, thank you for your attentions, and see you, of course, on the laboratory next week.
See ya.
Okay, bye-bye.